Hi, and welcome to another stop along our tour of the radio frequency spectrum. In this video, I'll be showing you an example of a digital television signal, that is DTV. In this case, one such signal which is centered at 551 megahertz. The DTV signal I'm showing in this video was received near Blacksburg, located in the southwest region of Virginia in the United States. I'm receiving this signal using a software-defined radio known as the AirSpy R2, which is connected to my laptop by USB. The antenna is a simple telescoping dipole, which is directly connected to the R2 with no impedance matching, no amplification, and no filtering. The noise floor in this demonstration is strongly dominated by the internal noise of this setup. I'm displaying the data in real time using the program GQRX running on Ubuntu Linux. The top panel is a spectrum display, that is, power spectral density is a function of frequency in megahertz. The display is in decibels, that is log scale. The bandwidth of my setup is 10 megahertz, and as you can see, the DTV signal takes up about 6 megahertz of that bandwidth. There's nothing special about this particular signal. It's merely one of about 10 or so that I'm able to receive at my location, and these signals appear in various subbands throughout the VHF and UHF band. Most television broadcasters in the US use what is known as the ATSC standard. In this standard, data is sent using 8 discrete magnitudes of the carrier. So this is amplitude shift keying with 8 symbols. And since there are 8 symbols, they're sending 3 bits at a time. And this scheme uses square root raised cosine pulse shaping, which yields the distinctive flat spectrum with sharp roll-off at the edges and low side lobes. In fact, here the side lobes are below the noise floor. The resulting signal is about 6 megahertz wide, here roughly 548 megahertz through 554 megahertz. You might notice a narrow signal poking out at a frequency just above 548 megahertz at the low end of the spectrum. That's known as a pilot signal, and that's intended to serve as a frequency and phase reference for the receiver. And of course, you've probably noticed that the spectrum of this signal is varying over time. To me, it looks like jello that's just come out of a mold, and so is jiggling around a bit. This is the result of multipath fading. Where I am, and anywhere you might receive this signal, you receive not one signal but multiple copies. We call that multipath. The copies are due to reflection from terrain. Now this signal is being received in the Blue Ridge Mountains of southwest Virginia, so there's lots of opportunities for signals to be reflected on their way to the receiver. And because these copies all took different paths, and the paths all have different lengths, the relative phases of the copies are different among themselves and vary with frequency. This particular phenomenon is known as frequency selective fading, and we refer to the maximum bandwidth over which the spectrum can be assumed to be independent of frequency as the channel coherence bandwidth. Now, the fading we see here is not only frequency selective, but also varying in time. And this is quite apparent in the waterfall display especially. You can see that the spectrum cannot be assumed to be constant for more than maybe a second or so, or maybe sometimes longer, and sometimes less. We call this time over which the spectrum can be assumed to be constant the channel coherence time. The reason for this time variation is simply because the phase of the multipath copies is varying with time. Now this could be for a bunch of reasons, but it's prevalent here because at this frequency, the wavelength is only about 54 centimeters. It doesn't take a whole lot of movement to induce tens of degrees of phase into the signal. If you want to try to reproduce this at home using a less expensive receiver in Microsoft Windows, my recommendation would be to purchase a RTL SDR V3 kit, which is about $40 US and includes an antenna. For software, I'd suggest the free-to-use program SDR Sharp from AirSpy. The disadvantages of that setup compared to what I'm using here will be that the bandwidth is limited to about 2 megahertz. So using that setup, you'll only be able to see a portion of the DTV signal at a time. Otherwise, you'll be able to repeat pretty much everything I'm doing here, including this clear visualization of the fading behavior. That concludes this brief observation of a digital television signal. Thanks for watching.